In this video, we're going to cover alternating series remainder, and then at the end of the video, we're going to cover absolute and conditional convergence. For an alternating series, what we can do is we could take a partial sum. So I'm going to work through the first example. I'll explain all of this through example number 1. So it's asking us to use a fourth partial sum. So I'm going to sum up the first 4 terms. So we get 1 minus 1/2 plus 1/6 minus 1 over 24. So again, this is asking me for the fourth partial sum. So this is the sum of the first 4 terms. I added these up, combined them, and I got 5/8. So this is an approximation. This is off by some amount than the actual value of the series. If I kept going to infinity, ... this would be the exact value. So I could say that the sum of the series is equal to the sum of the partial plus the remainder. Now, we're going to call all of this here the remainder. This is how far off I am from the actual value. So if I was to solve this for r, we can say the sum of the series minus the partial sum gives me my remainder. Now, how are we going to figure out our remainder? Well, the remainder, now if you look up here, it says it's the first neglected term. So let me explain that, and then I'll explain why. So if you were to add up the first 4 terms, the error will always be less than or equal to the first neglected term. So if I'm adding up the first 4 terms, the 5th term is the first neglected term. So you always want to go out one more term than what you're summing up. So I would have added one more term, which is 1 over 120. So that is what we call our error term. So I need the error will be less than or equal to 1 over 120. So that means that my sum, which is here, worst case scenario, it's off by 1 over 120. So we can bound it on the top, we can bound it on the bottom. So I could say my sum would be less than or equal to, I could say 5/8 plus 120. So that's bounded on the right-hand side, and then I could bound it on the left-hand side. 5/8 minus 120. This 1 over 120 is the worst case scenario. So let's kind of look at how that's even possible. What I'm saying is that this one term accounts for everything from here all the way to infinity. So how is that possible? Well, it only works because this is an alternating series and that it converges. Because it converges, it decreases in magnitude. So for example, I'm going to use whole numbers just to explain it to you, but let's say we had 10 minus 9 plus 8 minus 7 plus 6 minus 5 plus 4 minus 3 plus 2 minus 1. So let's say, for example, this is my first neglected term. I claim that all of this can never add back up to that. And it's twofold. It's because it's changing sign, but it's also because it's decreasing in magnitude. So if we do negative 9 plus 8, you get negative 1. Negative 1 minus 7 is negative 8. Negative 8, now, because you're going down in size here, plus 6, you're never going to get back to the 10. So this number here accounts for all of this. So all of this. So that next term is the first neglected term. Our error will always be less than or equal to that first neglected term. Okay? All right. So let's kind of work through it now. Right? What alternating series partial sum will have an error less than or equal to 0.001? So for a lot of these, it's best to just guess and check. So I have my a sub n, which is that, and I need that to be less than or equal to 0.001, which is 1 over 1,000. So I need to figure out what n value is going to make this be a true statement. So to start, I mean, you can almost look at it and know you're going to be in the 500 range. So I can say 2n minus 1 equals 1,000. We could say 2n equals 1,001. So n is equal to 500.5. So we're in the 500 range. If I plug in 500 to this, so let's look at that. If I plug in 500, we're going to get 1 over 500 times 2 is 1,000 minus 1 is 999. Is that less than or equal to 1 over 1,000? And I don't think that it is, because this would have to be bigger on the bottom. So this is when n equals 500. Now I'm going to do when n equals 501. So if n equals 501, I'm going to plug it into here again. So you get 501 times 2. We get that, and then we take away 1, so we get 1,001 less than or equal to 1 over 1,000. So this is in fact smaller. So that means that this is my error term. So the 501st term is my error term, which means I need to add up the first 500 terms. So the answer to the question is n equals 500 terms. Okay, for number 3, same premise. We want to show that 1 over n plus 1 factorial is less than or equal to 1 over 1,000. Because it's factorial, I'm just going to guess and check. You'll see as you get more comfortable with factorials, you're going to see that it grows pretty rapidly. So if we plug in 1, actually we have to plug in 0 to start. So we're going to plug in 0. So I'm going to plug in 0, I get 1. So when n equals 0, I get 1. So this will be plugging in 0, 1, 2, 3, 4, 5. I don't know how far out I have to go. So we get 1. When I plug in 1, I get 1/2. When I plug in 3 or 2, I get 1 over 6. When I plug in 4, I get 1 over 24. 5 is 1 over 120. 5 is 1 over 720. And then 6, so n equals 6, I get 1 over 5,000. So that's the first one. So this is the first time that it's less than or equal to 1 over 1,000. So this is my error term, which means I need to add up this many terms. So this is 1, 2, 3, 4, 5, 6 terms, but n is going to be equal to 5. Find an error bound 6 terms. So this one is asking me for the upper and the lower bound. So we're going to use the partial sum. So we get s sub 6. I'm going to plug in. We get 1 minus 1/2 plus 1/6 minus 1 over 24 plus 1 over 120 minus 1 over 720. So the partial sum here is 91 over 144, which I did this all with a decimal. So it was about 0.63194. So that's my approximation. My error term, so error term would be the first neglected term. Since it's 6 terms, that's the 7th term. So a sub 7 is 1 over 5040. So that tells me that this approximation is off by at most 1 over 5040. That's pretty accurate when you think about it. We only added up 6 terms. So my sum, it's going to be less than or equal to, so the 0.63194 plus 1 over 5040, and then 0.63194 minus 1 over the 5040. So the sum, I got 0.63214 and then 0.63174. Find an error bound, 6 terms, same as above. So S sub 6, we're going to get 1/4 minus 1/7 plus 1/12 minus 1/19 plus 1 over, so this is 1, 2, 3, 4, plug in 5, so 1 over 28, and then minus 1 over 39. I didn't calculate my sum, but I have the final answer, so I must have kept it in my calculator. The error term is the 7th term. So A sub 7 will be 1 over 52, which is about 0.01923. So my sum is going to be, so S sub 6 plus the 1 over 52, and then S sub 6 minus the 1 over 52. I did get a final answer. So this would be 0.16714, and then 0.12867. All right, last one, how many terms would be required? 0.01. So 0.01, first and foremost, is 1 over 100. So I have 1 over n squared plus 3n plus 5 less than or equal to 1 over 100. So I just randomly started. I picked a number. I think I started with 5. If n is 5, it's way too small. So then I went up. I chose 8. So let's say n is 8. We would get 64 plus 24 plus 5. I get 93. So if n is 8, we get 1 over 93 less than or equal to 1 over 100. So that's at n equals 8. So that is not true. To be smaller, the bottom needs to be bigger. So then I went up to 9, but I'm close. 9 is going to work. So n equals 9. Let's just confirm it. So we're going to get 9 squared. So 81 plus 27, 8, 9, 10, and then plus 5. It obviously works. So 8, 9, 10, so 113. So 1 over 113 less than or equal to 1 over 100. Now everything after n equals 9 is going to be smaller. 10, 11, 12. You have to find the first time that it's smaller. So n equals 9. That means this is my error term. This is my error. This is the error, which means I have to sum up the first 8 terms. So to answer the question, n equals 8. So here we have some AP style multiple choice questions. You have to get past all of the notation. It can be very confusing. The takeaway is it's alternating. If it's alternating and they want the error less than 3 over 100, okay, so we know we're looking at the first neglected term. What this is specifically asking is what k. So it's trying to find a partial sum. It's asking how many terms do I need to add up? What does k have to be so that this all happens? So they're giving us sort of a guide here because these are the values. Okay, so I'm going to plug in, so 2 over n, and I need it to be less or equal to 3 over 100. So I just started plugging in values. They started with 64, so I started with 63. So when you plug in 63, you get this. It's too big because 3 over 100 is 0.0300. So when I plug in there, I get, this doesn't work. And I just worked my way up. I plugged in 64. I'm getting closer. Plugged in here, 2 over 65, so I'm just going 63, 64, 65. Still bigger. 66, still bigger. Plugged in 67, that's the first one that's smaller. So that tells me this The 67th term is my error term, which means I need 66 terms to add up to get my sum. So that's why it's B. Same thing for number 8, alternating series, error partial sum, how many terms, so that I'm within 0.03. So it's 1 over root n, and I need it to be less than 0.03. And again, they're giving us the values here, so these are way off, which is why I started with this one, to see if I have to go this way or this way. If I do the 333, I'm way off, so I came up over here. So I plugged in this. This was, I don't have my calculator, but it was 0.0300, and it did have a number here, so that still didn't work. I had to go to the next term so that it was smaller. So this is the first time it's smaller. So again, this is my error term. So that was 1,112, which means I need 1,111. For number 9, same idea. We have 9 over 10,000. So I have 1 over n squared. Oops. And I want it less than or equal to 0.0009. Again, they're giving us the terms. This one's a little bit more difficult because these are really close together. So I started with the 31. I got 0.001. I plugged in 32. I got 0.00097. So we're getting close. Plugged in 33, 0.0092. Still not there yet. This is the first time when I plugged in 34 that it was smaller. So this becomes the error term. So it was 34, so that's why I need to add up 33 terms. And then the last one, number 10. What is the alternating series error bound? So they're just asking us what is the error. So it's the first neglected term. If we're adding up 15 terms, it's the 16th term. So I need a sub 16. So a sub 16 would be 1 over 2 times 16 plus 1. So 1 over 33. The last part of this video has to do with absolute and conditional convergence. I'm just going to introduce it. When we do the examples in class and some of the practice, I'll show you when you want to use this sometimes. So you have to do it if they ask you for absolute convergence. But sometimes you'll get this weird series where if you took the absolute value, it made it much easier, maybe it will work, okay? But for right now, I'm just going to run through what it is. So absolute convergence means you take the absolute value of your series. So you take the absolute value, you need to show me that on your test, and you're going to get a new series. If that series converges, we say it absolutely converges and you're done. It's the strongest type of convergence. And the reason it's the strongest is here. Look over to the right. If you have an alternating series, so let's say we have this, and it converges. Let's just say it converges. If you take the absolute value of this, so you took the absolute value, you're going to end up with all positive values. If you can show that this converges, this is harder to show convergence because everything's positive. Think about that for a second. Think about how hard it is to show something converges if all you're doing is adding. If you can show that this converges, we can make the conclusion that the alternating one has to converge because this is alternating signs. So let's run through the examples here. Again, we're going to take the absolute value. So if we take the absolute value, so we're going to get a new series. So n equals 1 to infinity, 1 over n to the 2/3 power. This is a p series. P is equal to 2/3. So this diverges. So if this diverges, we need to go back to the original. I'm going to rewrite this. And I'm going to test to see if the original converges. Now, to be honest, if it's alternating, most alternating series converge. It's so easy to prove. All we need to do is show that the limit as n goes to infinity of 1 over n to the 2/3 equals 0. And then I need to show that a sub n plus 1 is less than or equal to a sub n, which is true for this. So this converges so we call this conditional convergence. So when the first one diverges and the second one converges, we say this converges conditionally. And we'd say by AST. Okay, for this one, take the absolute value. We're going to get a new series, so n equals 1 to infinity, 1 over 3 to the nth power. It's geometric. R is 1/3, which is less than 1, so this converges absolutely. For number 3, take the absolute value. We get a new series, so n equals 1 to infinity, 1 over n squared. I look at this independently of the one from above it. It's my new series, so it's 1 over n squared. P is equal to 2, which is greater than 1, so it converges absolutely. Here, you should be familiar with both of these, okay? You're going to see them often. Alternating harmonic converges, harmonic diverges. But let's do it. We take the absolute value, so we get the harmonic when we do that. So n equals 1 to infinity, 1 over n. P equals 1, so this diverges. Okay, so we move on to the alternating series, so negative 1, n minus 1. And again, most alternating series converge because it's such an easy test to prove. So if we do the limit as n goes to infinity of 1 over n, as long as it equals 0, and we know that 1 over n plus 1 is less than or equal to 1 over n, which is mostly true, it's going to converge. So this converges conditionally by AST. And last here, this part is the alternating part. If you plug in the values, you're going to get negative 1, 1, negative 1, 1. So this is all just negative 1 raised to some power. So it's just the alternating part of it. So we can take the absolute value, which is nice because it gets rid of all of that. So we're going to get n equals 1 to infinity, 1 over n to the 7 halves. P is equal to 7 halves, which is greater than 1. This absolutely converges, we would say, by P series.